Okay, let's get this one underway. So, standard procedure here. This is the 2023 spring one. Okay, question number 1. Find the relative. Actually, you know what? Let me do a preface right here. Preface. Not all topics covered on current 2025 exam. Some of these topics that you might cover here are similar to the topics covered in the upcoming exam, but they're not the same. For example, question 1, find the relative extrema. Now, this is from the first exam, actually, so this is not a Lagrange multipliers question. Instead, this is one where you have to find the discriminant d, which is equal to the double partial of f of x, the double partial of y f. Those two are minus, and then minus the mixed partial of xy squared. If you remember that, then you should be fine, but let's go through the steps anyways. So the gradient of f in this case will be, put the 3 there, which just gets you negative 2x squared plus 4y. Okay, the gradient at y would just be 4x minus 4y. Okay, so now what we have to do is we have to find when the partial derivative of f at x and the partial derivative of f at y are equal to 0. So in this case, set them equal to 0. Set this equal, whoopsie daisy, that should be a minus. Set this equal to 0. So what will this turn into? Well, I'm going to make this into negative 2x squared equals negative 4y. So x squared is equal to 2y. So, oh wait, actually, we can make this a bit easier. We'll just say that 4y is equal to 2x squared. So in this case, y is just equal to 1/2 x squared. That's a bit easier for us to do, so let's stick with that. And for this one, I'm going to factor 4 out, so we get 4 times x minus y equals 0. So in this case, this just becomes 0, and this becomes x equals y. So if we now plug this in here, you get x is equal to negative 1/2 x squared, which gets you 2x is equal to x squared. So 2x minus x squared equals 0. So if I take this out, I get x equals 2 minus x equals 0, in which x will either be equal to 0 or it will be equal to 2. So now that we have our 2x points, let's plug them back into here. So since we know that, I'm going to use a different color. Since we know that x is equal to y, we can say that our critical points are at the point 0 for x, 0 for y, and then 2 for x, 2 for y. So these are our 2 critical points, 0, 0, and 2, 2. Okay, now what we're going to do is we have to set this up. So our f of x, our double partial at x will be equal to this, so that would be negative 4x. Our double partial at y will be equal to negative 4. Our mixed partial will be equal to 4. So let's set this up. Negative 4x times negative 4 minus 4 squared. Okay, so now let's evaluate them. At 0, 0, and at 2, 2. So let's do that. Okay, so at 0, 0, we plug in a 0. You get 0 for that times negative 4, which all cancels out to 0, minus, this will become 16, so you get negative 16. Now, let me remind you of the rules. Remember, if the discriminant, in this case, this d, is less than 0, that will become a saddle point. If the discriminant is equal to 0, it is inconclusive. And if d is greater than 0, then you have an extrema. So that will be min or max. Okay, so in this case, we see it's less than 0, so we know that's just a saddle point, and nothing in here has a saddle point, and saddle points are not relative extrema, so you don't even need to know that. And so if you plug it into 2, you get negative 4 times 2 times negative 4 minus 16. So in this case, this will become negative 8 times negative 4 minus 16, which is equal to 32 minus 16, which is 16, which becomes a relative extrema because it is greater than 0. Okay, so now, or to find if it's a min or a max, let me go back up here. If the double partial at x is less than 0, that's a max. Double partial at x is greater than 0, that's a min. So let's see. The double partial, which is this here, is equal to negative 8, which in this case is less than 0, so which makes this a relative max. So which one is here? Let's first take out answer choices. That's not our point, not our point, not our point. Our point is at 2, 2. This is a relative minimum, so it can't be that. So our only answer choice left is E. In this case, that is correct. Smiley face. Okay, number 2. Consider the surface. Z equals 3 minus x squared minus y squared plus 4y. Find the points on the surface at which the tangent plane is horizontal. Okay, so this is going to be a really crappy drawing, but how I want you to imagine this is the tangent plane is basically where, this is really weird to draw, but it's where x and y are equal to 0. Or should I say, df dx dy, df dy are equal to 0. So let's find the partials. So df dx in this case is equal to negative 2x, and df dy is equal to negative 2y plus 4. Okay, so now we have to set these equal to 0. So negative 2x, when it equals to 0, x is simply 0. When negative 2y plus 4 is equal to 0, y is just equal to, well, that becomes negative 4. Negative 4 divided by negative 2 is just 2. So now, all you have to do is plug in to z. So now we know that z is equal to 3 minus 0 squared minus 2 squared plus 4 times 2, which becomes 3 minus 4 plus 8, which is negative 1 plus 8, which is equal to 7. So now we know that our points will be 0, 2, and 7. So our final point is 0, 2, 7, which is answer choice B, which in this case is correct. Okay, moving on. question 3. Now this is a Lagrange multipliers question. This is what we are all familiar with, and we've already done many of these, so I hope you've become accustomed to the protocol we normally do. Remember, take the gradient at f, which is 1, 1, 1. Take the gradient at g. Remember, this is our f, this is our g, which in this case is 2 times x minus 1, 2y, 2z. And then set the gradient of f equal to lambda, the gradient of g. Remember, lambda is just any constant. It can literally be anything in this case. So we know that 1 is equal to lambda 2x minus 1. 1 is equal to lambda 2y. 1 is equal to lambda 2z. Now I'm going to first deal with these two. If you do the thing where you divide them, you get this thing right here. These cancel out, these cancel out. You simply get 1 is equal to y over z, which means z is equal to y in this case. And then what we can do here is, if I look at it, we can see that in this case, x minus 1 is equal to 1 over lambda 2, just like how y is equal to 1 over lambda 2 if you just divide by lambda 2 for both of these, which means that z is also equal to lambda 2, which means that z is equal to y, which is equal to x minus 1. Okay, so now we have these. So what am I going to plug into here? Well, I'm just going to choose something simple. Let's just say z. So in this case, we say that you plug in z for everything. Z squared plus z squared plus z squared is equal to 1. Now you may be thinking, why is it a z squared, not like a z minus 1? Well, remember, x minus 1 is equal to z, so it's the full thing. So in this case, 3z squared is equal to 1, which means that z squared is equal to 1/3, which means that z is equal to 1 over root 3, or just root 3 over 3. Okay, so now that we know that z, this root 3 over 3, is also equal to x, which is also equal to x minus 1. So we can simply say that z is equal to root 3 over 3, y is equal to root 3 over 3, and then x minus 1 is equal to root 3 over 3, so x is equal to root 3 over 3 plus 1. Now, all we have to do is plug in back to our f right here, which is just simply x plus y plus z. So if we plug this in, root 3 plus, I should probably put this, simply get root 3 plus 1 plus root 3 plus root 3. So what I'm gonna do here is I'm just gonna say root 3 plus 3 plus root 3 plus root 3 plus root 3 plus root 3. This may look like it's just escaping PEMDAS, but it kind of is, but it comes out with the same answer. So the 3's go away, and you simply get root 3 plus 1, which in this case is the same as answer A, which is our correct answer. Okay, moving on to question 4. The x-coordinate of the point on the plane z equals x plus y that is closest to the point 1, 1, 1 is equal to. Now this is actually another Lagrange question, but it uses the distance formula. Now remember, the distance formula is d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared plus dot dot dot. It goes on for forever. But in this case, it's just gonna go to z. So how do we set this up? Well, in this case, d, I'm just gonna actually square it. I'm gonna square this, bring it over here. D is equal to x minus 1 squared plus y minus 1 squared plus z minus 1 squared. So this is our distance formula, which in this case is also equal to our f. So if you watch the video, I think it's for, I can't even remember at this point. I think it might be 2019 or it might be spring 2025. This same kind of question pops up. I think this one is a little bit easier than that one just because it's only using a much smaller constraint right here of g. But this is how you generally want to set it up. So how do we do this now? Okay, so now that we do this, we want to find, I guess, the x chord of absolute min. Okay, so let's do this. Let's take the gradient at f, which in this case is 2x minus 1, 2y minus 1, 2, whoops, that should be a 2, z minus 1. And our g in this case will just be, let's convert this g to x plus y minus z equal to 0. Will just be 1, 1, negative 1. So we know that 2x minus 1 is equal to lambda times 1 in this case. So 2y minus 1 is also just equal to lambda. And 2z minus 1 is just equal to negative lambda. So in this case, what do? Well, we just set them equal to each other. We know that 2 of x minus 1 is equal to 2 of y minus 1 because they're both the same lambda. These 2's cancel out. You get x minus 1 is equal to y minus 1. These 1's will cancel each other out, so we just get that x is equal to y. And if you look at this, you'll also see that in this case, if you want to find what negative lambda is, you can just take the negative version of either of these. So in this case, I'm just going to say is that 2 of z minus 1 is just equal to negative 2 of y minus 1, which would mean that in this case, z minus 1, if I move the 2 over here, just becomes negative y minus 1. So z minus 1 would be equal to negative y plus 1. So z in this case is just negative y plus 2. So when we plug this back into our constraint, we just get that, hold for a second while I color this in. We just get that negative y plus 2 is equal to, in this case, x is equal to y plus y. So negative y plus 2 is equal to 2y, in which 2 is equal to 3y. So y is equal to 2 over 3. Now, I don't actually need to evaluate any further because x is equal to y, which means that x is also equal to 2 over 3. And if you notice, this is actually our only critical point. In this case, this is the only critical point we have to evaluate that we have. So in this case, the x-coordinate of the point on the plane that's closest will just be 2 over 3, which is b, which in this case is our answer. So make sure to watch out for those things. Okay, 5. Find the average value of the function f of x squared, f of xy equals to x squared y over the region R, where R is the rectangle with vertices -1, 0, -1, 5, 1, 5, and 1, 0. So how do you find the average? Well, let me show you. You take the double integral of the region, dA, and you divide it by 1 over the area. So let's take this step by step, right? I noticed that this has a negative, so we're going to need both sides here. So we got negative 1, 0, negative 1, 5, 1, 5, 1, 0. You might be noticing I'm not using my usual blue. And I just noticed that too. That makes me sad. Let's use blue. So let's see. This will become 1, 5, negative 1, 5, 1, 0. Sorry, negative 1, 0. That'll become negative 1, 0. Sorry, 1, 0. So you know that this side length is 2. This side length is 5. So based on this, you already know our area, which is just base times width, will be equal to 2 times 5, which is 10. So what are our bounds? Our bounds are also pretty easy, pretty simple. In this case, since it's literally just a rectangle, let's take them in our Cartesian dx dy coordinates. So from x, it'll be from negative 1 to 1. From y, it'll be from 0 to 5. Remember to keep that 1/10 out there. And it'll be x squared times y of dx dy. And if you evaluate this, you get x cubed over 3y from negative 1 to 1, which gets you 1/3 minus, this will become negative 1/3, which becomes 2/3 y. 2/3 y evaluated from 0 to 5 gets you y squared over 2. 0 to 5, gonna multiply this by 2/3 eventually. So you get 25 over 2 minus 0, so just 25 over 2. 25 over 2 multiplied by 2 over 3 will just get you, will just get you 25 over 3 again. sorry, 25 over 3, not again. Okay, so now that you have 25 over 3, well, the last thing is just to multiply it by 1 over your base area, which is 1/10, which means you get 25 over 30. And in this case, if we simplify it, let's say we divide by 5, you just get 5 over 6, which in this case, 5 over 6 is our answer D, which in this case is the correct answer for number 5. Okay, number 6. Evaluate this double integral at the region of f of xy equals to sine x over x dA, where R is the region and the xy plane bound by the x-axis, the line y equals x, and the line x equals 1. So how am I going to evaluate this? If I say the x-axis, I'm just going to say that means y is equal to 0. We already know that y is equal to x and that x is equal to 1. So let's draw this out. Integrate with respect to y first, then with respect to x. You can't tell me what to do, but we should probably still do what they tell us to do. So y goes from here, y equals 0 to here, y equals x, and then x equals 1. And these are our regions here. Okay, so how do we integrate this? Well, let's write out our bounds first. If we integrate with respect to y first, it'll be from 0 to x, and from x, it'll be from 0 to 1 of sine x over x times dy dx. So if you evaluate this, you simply do y sine of x over x from 0 to x, which gets you x times sine of x over x minus 0, which in this case, these x's will cancel out. You simply get left with sine of x. If you evaluate from 0 to 1 of sine of x dx, that just becomes negative cosine of x from 0 to 1, which gets you negative cosine of 1 minus cosine of 0, which in this case just produces negative cosine of 1 minus 1. So, oh, sorry. Oh, whoops, no. Should not be minus cosine of 0. It should be minus negative cosine of 0, which means you get negative cosine of 1 plus 1, which in this case, I'm just going to rewrite to equal 1 minus cosine of 1, which in this case is our answer choice A, which is the correct answer for number 6. Okay, halfway through, guys. Number 7. Rewrite the integral as an iterated integral in polar coordinates, but do not evaluate the integral. Okay, so I'm going to show you a neat little trick to instantly get a few answer choices out the way. So we all know that if you're looking at this, x squared plus y squared is equal to r squared. Now, if we do square root of r squared, which is just 2 times 1/2, you just get 1. You just get left with 1. And remember, this dx dy turns into r times dr d theta. So if we multiply this by r dr d theta, our initial, what do we call it? Our f is just going to be r squared dr d theta. That should be what we're evaluating at first. So look at your answer choices and eliminate any ones that do not have the dr d theta. This one doesn't have a dr d theta. Sorry, an r squared. This one does not have an r squared either. It appears my roommate just dropped something. Hi, Brady.
Sorry, Steven.
Shout out to Brady. He's the GOAT roommate. Okay, but anyways, this is r squared, this is r squared, so we can keep both of these for now. Now, this says dx, right? So if we look at this, we know that x is equal to, is from negative 1 minus y squared to x to 1 over y squared. So we know that x is equal to the square root of 1 minus y squared, which means that x squared is equal to 1 minus y squared, which means that x squared plus y squared is equal to 1. So r squared is equal to 1, which means that r is just 1. Now, you might be wondering, Steven, both of them go from 0 to 1, and you are right. But you should still know how to do this because it's important for other things. But you're right, we should move on to looking for thetas. So we're going to move on to our second integration, which is y is bound between 0 and 1. So know that y is always less or equal to 0. So what does that look like on our graph, right? That means in our graph, y can only be between this axis, axis number 1 and axis number 2, because this is where y is positive. But if we move that to Cartesian, to polar, that's from the angle 0 to the angle pi. So our bounds are from 0 to theta, from 0 to pi. So C has 0 to pi, which means that our answer is C, which is correct for number 7. Okay, number 8. Reverse the order of integration in the following iterated integral and evaluate. You know how we got to start these? We got to draw. Okay, so this goes dx dy, and in this case, dx goes from 1/2, whoopsie daisy, let's stick with my original color, 1/2 y to the square root of natural log of 3. So 1/2 y would look something like this. This would be x equals 1/2 y. And let's just say root 3 is somewhere in here. Sorry, not root 3, natural log, square root of natural log of 3. And then y is bound between 0 and 2 times the natural log of root 3. So I'm gonna say whoopsie daisy, that was way too high up. I'm gonna say like right here, where y is equal to 2 times the square root of natural log of 3, and it's in this area right here. So how we're currently going, it goes from this line to here, but let's move it from this line to this line. So in this case, we know that 1/2 y is equal to x. So let's just rewrite that as y is equal to 2x. So if we see, now y goes from this point, which is y equals 0, to here, to this line, which is y equals 2x. So our new integral will be from 0 to 2x, and x just goes from 0 here, let me put my pointer, 0 right here, to x equals square root of natural log. Man, I'm really messing this up. From 0 of square root of natural log of 3. And the inside stays the same. It would just stay as e to the power of x squared. But now we're going from dy to dx. So, same integration types. Y times square root of ex from 0 to 2x gets you 2x e to the square root to the power of x squared, and that'll just be minus 0. Now, we got to evaluate from 0 to the square root of natural log 3 to x times e of x squared. We're going to do some u substitution, where u is x squared and du is 2x. So in this case, that takes out this 2x, and you get left with eu. But we got to reset our bounds. So if you do square root of natural log of 3 squared, you just get natural log of 3. And if you do 0 squared, you just get 0. So now that we have that, we get simply left with the integral. Wow, there's a very loud car outside my window. From 0 to natural log of 3. In this case, let me bring this up here. This just gets you e to the power of natural log of 3 minus e0, which is just 1. So you get e natural log of 3 minus 1. Now, if you don't know this fundamental theory, know it already, e, if it's to the power of a natural log, it is just equal to whatever variable is in that natural log. So in this case, that's just 3. So you get 3 minus 1, which is equal to 2. In this case, that's our answer E, which is the correct answer for number 8. Okay, number 9. Convert to cylindrical coordinates and evaluate. So cylindrical, that's our z, dr, d theta. Well, it'll be rz. Oh my lord, I messed that up. It'll be r dz dr d theta, not just z. Okay, so let's evaluate this step by step. First with z. So z is from 0 to square root of x squared plus y squared, which means that in this case, z is equal to the square root of r squared, which is just r, and it's also 0. Since dz is already there, I'm just going to keep it where it is, and it'll just change from square root of x squared plus y squared to from 0 to r. Now, moving on to dy. Now we know that y is bound between 0 and square root of 100 minus x squared. So if y, in this case, is equal to 100 minus x squared, then we can say that y squared is equal to 100 minus x squared, which means that x squared plus y squared is equal to 100, which means that r squared is equal to 100, which means that r is equal to 10. So our bounds will run from 0 to 10. And finally, our theta. We know that x is bound between 0 and 10, my god. Which in this case, if you look at it, since x must always be positive, it'll only run through the first quadrant, which is pi over 2. So it'll run from 0 to pi over 2, and our integrand right here, I recently just learned that it's called an integrand, which is where the I comes from, I for integrand. That's just a lie. Sorry, that is just not true. I don't know why I lied. This will just become 1 over the square root of r squared, just 1 over r. So it'll be 1 over r times r dz dr d theta, which in this case, our first thing will just become, these just become 1. So you get 1 dz, which gets us z evaluated between 0 and r, which just becomes r. If we evaluate from 0 to 10 of r, you get r squared over 2 from 0 to 10, which gets you 100 over 2 minus 0, which is just 50. And then if we evaluate from 0 to pi over 2, 50 d theta, you simply get 50 pi over 2, which in this case is just 25 pi. In this case, 25 pi is our answer D, which is the answer for number 9. Okay, number 10. Let V be the volume of the solid bounded the surfaces. That seems weird. Bounded? Okay, I think it should say bounded between the surfaces z equals 6 minus x squared minus y squared, and z equals x squared plus y squared. If this is our big volume, what is A and B? Now, first thing, it starts at dz and already says x squared plus y squared. That's this one right here. So B has to be this one. So B has to equal 6 minus x squared minus y squared. So let's find all the ones where 6 isn't equal to that. So in this case, where B isn't equal to that. So in this case, B is not equal to that. B not equal. B not equal. So it can't be D, it can't be B, it can't be A. So we got to evaluate which our A is. Now the next one we see is dy. So how do we evaluate from here? Well, we know that z is equal to 6 minus x squared minus y squared, but z is also equal to x squared plus y squared. So if we set these two equal to each other, like so, we can say that in this case, we want our y, so we want to isolate y. So let's move everything to where it should be. So if we move it over here, we get 2y squared is equal to 6 minus, is equal to 6. In this case, it's just 6. Oh, wait, am I wrong? Oh, wait, I am wrong. Whoops, whoopsie daisy. It just should be 6, minus 2x squared. So now what we do, just divide by 2. So you get 3 minus x squared equals y squared. So in this case, y is equal to the square root of 3 minus x squared. So it'll be bound between whatever's already there, which is this one, and we gotta find A. Okay. So in this case, it'll just be C. Now C has the negative right here, but in this case, it'll just be between the negative and the positive, because in this case, it'll just be a circle. Because remember, if we set this equal to y, you just get x squared plus y squared equals 3, which means that r equals the square root of 3. So these are just circles. Okay, a little bit weird, but you got through it. Okay, which of the following integrals represents the volume of the solid inside a sphere of radius 2 centered at 0, 0, 2, and outside a sphere of radius centered at 0, 0, 2. Now, you might look at this and be like, what is going on? But this is a spherical question, and allow me to like kind of draw it out how it kind of looks, right? So you have this first sphere, and it goes at around 0, 0, 2, and then it has a radius of 2. So it kind of looks like this, yeah. And then you got this second sphere, and it's just at 0, 0, and then it has this radius of 2 as well. And then we're trying to find like what's inside of this area. So that's a very poor drawing, but we're trying our best. I can't draw. Okay, but how do we interpret these points right here, right? So you remember the distance line we just used? It's very similar to that. But do you remember how when we do a circle, it's x squared plus y squared equals r squared? Well, in this case, it's just the same, but we add a z. So it's x squared plus y squared plus z squared, which will be equal to phi squared. In this case, it's the same for this. Phi, you can think of phi as just like a radius, right? So if we set it like this will become x squared plus y squared plus z, but since it's 2, you minus 2, and that's all squared, which in this case is equal to 2 squared, which will be equal to 4. So that's our first equation. Let me clean that up. It'll just be equal to 4. And this will simply just be x squared plus y squared plus z squared equals 4, because it's also just radius 2. Now, why is it minus 4? It's not minus 2, not plus 2. Well, if you go up, it'll always be minus, down, it'll always be plus, right will always be minus, left will always be plus. Remember that from very early geometry. So, what are we going to do from then? Now, we got to convert. Remember that x in this case is equal to rho sine of phi cosine theta. Y is equal to rho sine phi sine of theta, and z is equal to rho cosine of phi. Remember these. They're so important to know. And now we got to convert them. So let's convert this one first. So this will become rho squared sine squared of phi cosine squared of theta plus rho squared sine squared of phi sine squared of theta plus we gotta do some factoring here. This will become z squared minus 4z plus 4 equals 4. So this will become a 0. So in this case, we just get left with sorry, I had to take a little wrist break right there. Okay, back to it. In this case, you know that you have your cosine theta here, your sine theta here, and these two are the same. So you can factor out rho squared sine squared of phi to get cosine squared theta plus sine squared theta, which just becomes 1. So you get rho squared sine squared of phi, and that would be plus z squared is rho squared cosine squared of phi, and this will be equal to 4 of rho cosine phi. Okay, so in this case, we take the rho's out. You get sine squared phi plus cosine squared phi, just becomes 1 again. So you get rho squared is equal to 4 rho cosine of phi. Man, having to say these all the time is really getting tiring. Okay, but if we divide by 5 for both sides, you get phi squared, rho squared over rho, oh my lord, equals to 4 cosine phi, which gets you rho is equal to 4 cosine phi. Now, finally, we know that that is one of our bounds, so we gotta take out everything that does not have that. That does not have it, it's a 4 sine phi. That's also a 4 sine phi. This doesn't even have anything relating to this. And we get these two. So now we got to see the other integral. But this one should be pretty simple, because just remember, plug these in. Remember that x squared plus y squared will usually lead you to just rho squared sine squared of phi. So in this case, I'm gonna miss out on writing all this because it's just so much. And z squared is the same as just rho squared cosine squared of phi, which will just be equal to phi squared. In this case, phi squared is just equal to 4, so phi is equal to 2. So now we know it's bound between 2 and 4 cosine phi, which is why our answer is A. That is for question 11. Wait, no, did I not do question 10 smiley face? Oh no, question 10 is C and I didn't do a smiley face. Sorry. Okay, question 12. Find the x-coordinate of the center of mass of a plate in the shape of a region bounded by y equals x, y equals 1/2 x, and x equals 1 with this density. Recall the mass moments about x and y are this and this, respectively. Okay, so how do you find the center of mass? So the center of mass is equal to this thing, x bar, y bar, in which x bar is equal to my over the mass, and y bar is equal to mx over the mass. So how do we find mass? Well, mass is equal to the double integral of this thing. It looks like this, but they always draw it as the same as the rho symbol, so I do the same thing. And that'll be from, well, dx dy, or switch around. Who really cares? In this case, I think I'm going to use dy dx probably. And in that case, if we draw this graph, it goes from y equals x and y equals 1/2 x, and then we got x equals 1, so it runs in this little area right here. Wow, that's a really bad drawing. So the x bounds will be from 0 to 1, and the y bounds will be from x over 2 to x, and we already know that our density is 2x, and it'll run from dy to dx. So let's evaluate this. This will become 2xy from 1/2 x to x, which becomes 2y squared minus x squared, which just gets us x squared. And then from 0 to 1, x squared, you just get, this should be a dx. Will get you x cubed over 3. Why did I change my voice? From 0 to 1, which gets you 1/3, which is equal to the mass. So the mass is equal to 1/3. Now, they want us to find the x-coordinate. That's our x bar. And if we see our x bar is equal to my over m. So what is my? Well, my is equal to actually the same integral, except we add in an x. And if it's mx, you add in a y. So in this case, from dy dx, now we start with 2x squared y from x over 2 to x, which gets us 2x cubed minus x cubed, which just gets us x cubed. And then from 0 to 1, oopsie daisy, oh my lord, from x cubed dx, we get x to the 4th over 4 from 0 to 1, which returns 1/4. Okay, So now we have our mass is equal to 1/3, our my is equal to 1/4. In order to find our x bar, we simply do my over m, which in this case is 1/4 over 1/3. Keep, change, flip. You get 1/4 times 3 over 1, which gets you the answer 3 over 4. So we know that our x coordinate for the center of mass is 3 over 4, which in this case is answer choice D, which is our final answer for the 2023. Now, it is Friday. We are very near to our second exam. I hope you have been studying a lot. If you've been using this as a study guide, thank you. If not, I hope you're doing good. I hope you continue doing your practice exams, looking over some stuff, and I hope you learned a lot of good math today. Thank you, and have a good day.